Okay, hello everyone. Good evening, I guess. So let me turn on my video just for a moment. I welcome you to the session. Okay, I'll keep the video on for a little bit. Sometimes it helps to see my impressions, and so that could be helpful. So let me just do that. Okay, so let me make it a full screen and speak to you for a little bit. Okay, so I hope you're doing well, and things are okay here, and we're trying our best to survive through this period. Things are not looking very good outside, but we have to take care of ourselves and just stay strong, I guess. In the meantime, we have to worry about our course, so we just have to keep doing what we are doing. So today, the main thing I want to talk about is the few things here. First of all, you can find these class notes on Sakai. So if you want the same notes that I have, you can find them on Sakai. And I'm assuming that you're working on the try assignment. Just want to remind you that there's a preliminary grading of your try assignment tomorrow night, April 1. And the assignment is formally due on the April 3rd. And also last day to hand in is April 5th. So make sure you keep track of those deadlines, because sometimes we tend to forget these things, especially since we don't meet anymore. And the grade report will say whether your code compiled. If it did, it'll give you a score out of 80. So if your score is 80, then that means you passed all the test cases and you don't need to make any more submissions. Do you have any questions there? Okay, so the midterm is going to be April 5th. It's a take-home offline exam. It will cover BST and AVL trees. And to study for the test, you should take a look at the problem sets 7 and 8. You can watch some videos or do some readings. The format is that you're given an MS Word document, which you will fill in the answers and submit a PDF through this new program called Gradescope. If you haven't done that, you can, you should try to learn this as soon as possible. It's very easy to kind of go through this. Any questions? Okay. So whatever the PST and AVL trees cover, those are the problem sets that you need to study. Okay, so learning goals for today. We're going to be focusing on our data structure called priority queue, and it's implemented with heaps. And we talked about the min heaps and max heaps. And these are the things that you need to be able to do. Describe the applications of a priority queue. Describe the invariants. Invariants are the things that don't change. So in other words, we talked about two things, shape invariant and order invariant. Be able to know how to insert a set of keys into a heap data structure. Be able to delete the minimum from a heap. When I talk about heaps, it could be min or max, but usually default is min heap. We also need to learn how to count the operations required to insert a new key, and also be able to count the operations required to build a heap. Okay. All right, so let's talk about heap invariance. Shape invariant means that heap is implemented as a complete binary tree. What we mean by complete binary tree is essentially that it's a tree that has all the levels full, and except for the last level where it's filled from left to right. The odd invariant means that given a heap with element A here, B here, C here, the A is less than or equal to B or C. So that's called a min heap because that root or the parent node is less than or equal to either one of their children. Do you have any questions so far? Okay, so let's move on. So the next thing is to talk about representation using a compact array. So for example, if you have a heap like this, let's say we have 2 here, 5 here, 4 here, maybe 6 and 7, 8, and this could be 7 as well. Now note that the heap can have duplicate elements. So it's okay to have duplicate elements in a heap. And the compact representation is essentially we can represent a heap using an array where the parent is, if parent is a of I in the array, we start from 1. And the 2 and the 3, the left child is a of 2I, and right child is a of 2I plus 1. So if I equals 1, you will have 5 and 4 here. Those are the children of 2. And the children of 5 are going to be 6 and 7. Notice 5 has index 2. So children of 5 are going to be at 2 times 2, which is 4. So 6 will be here. And then 2 times 2 plus 1, that's 5. And that's going to be 7 here. So these are the children of 5. And the children of 4 are going to be the next thing, which is 7 and 8. They are at 6 and 7 indices. Because if you notice, 4 has an index 3. 2 times 3 is 6. And 2 times 3 plus 1 is 7. Okay. All right. So let's talk about building a heap, building a min heap. So building a min heap is, I'm going to give you an example. Let's say you have 12, 20, 12, 14, 15, and 5. So I'd like you to just take a little bit of time and see if you know how to build this min heap. And while you're doing it, you can also count operations. Okay, so let me just start doing it. So the first thing we're going to be doing is that we put 20 into the root of the tree or the heap, because that's the smallest so far. And then comes 12. So 12 goes to the next available location in this heap. But because 12 is less than 20, you have to always compare with the parent. By comparing it, you're going to have one compare, and you're going to swap the 20 and 12 because the min heap, the parent, is less than the child. And now comes 14. So we have taken care of that. Now comes 14. You're going to insert 14 here. Now, because 14, you do one comparison with 12, no need to swap. And so you're just going to leave it like that because it's a min heap since 12 is less than 20 or 14. But you still have to do one compare. In fact, you can say the first one is going to be one compare and one swap. So let me write, yeah, that's fine. Let's just do the compare. Okay, then we have 12, 20, 14. And the next thing comes, which is 15. 15 always goes to the next. Notice, remember, it's a complete tree, so it needs to go to the next available place in the array. And now we do a comparison, 15 and 20. Because 15 is less than 20, you're going to be swapping these two. So we did one comparison there. And now you compare 15 and 12. And 15 and 12 is 15 is less than 12, so it's fine. So but you still did one comparison here. Okay, and so what we have now is 12, 15, 14, and 20. So the next thing comes, which is 5. 5 goes to the next available location. And now we compare 5 and 15. Because 5 is less than 15, you're going to swap it. So that's one comparison. So 5 comes here, 15 goes here. And then you compare 5 and 12 and do a swap. So that's going to be another comparison. So finally, we have 5, 12, 14, 20, and this is 15. So now if you look at this, that is a min heap. So if you count the total operations, we have, it's going to be 6 comparisons. Okay, so there's a question here. It says, can we just sort the array before making the heap? No, we don't want to do that. Why? It is less efficient, exactly, because sorting requires n log n. The reason we don't, otherwise we could just sort it and take the minimum. Plus, there's another reason for that. The other reason is that the heaps are used for dynamic data structures. That means things keep coming. So you don't want to keep sorting things, because every time you sort it, the best you can do is n log n. So because of that, you don't want to sort it. You just want the minimum. That's all you care about. Yeah, so you don't want to sort it unless it's a fixed element, a fixed size array. That might, if it's a fixed size array, it might be okay. Okay, now we got the question. So what I will do is I will turn on the poll here. Can you guys see it? There's a question about what are the practical applications of heaps. One of them is the Huffman tree. And there are many others. There are a lot of things like packet switching, internet routing. It's amazing number of applications with this heap data structure. Okay, let me turn on the poll here. So we have 4 questions. So I'm going to start a poll here. Okay. Note that it's asking the question. Yes, not. Okay. It's a max heap. All right, once you guys finish this, I'll publish the polling results. Okay, so I have 59 responses so far. Okay, maybe I'll publish it right now, and we can start to work through this to see who got this right. Okay. Okay, so based on the poll, it seems like most of you picked B. Okay, let's see whether B is the correct answer. Yeah, so it's fine. So is B the correct answer? So here's the B. B is a heap with all elements the same. It actually does represent a heap. This is a heap. Because if you keep in mind that the heaps can be equal, elements can be equal. I said less than or equal to or greater than or equal to. In this case, we are asking a max heap. Although this has all the elements the same, it is a heap. So B is not the correct answer. Okay, I'll publish the poll again, see if you can pick the right answer this time. B is now one of those. You have to choose from A, C, or D. Once we hit 60, I will start to discuss this. Okay, so let's take a look at this now. Now you say D. All right, so let's take a look at D. So in D, we have this thing, is it a max heap? So we can check that. So all you have to do is just draw this 30. These are the children, 27 and 23. That's okay. So that's a heap so far, max heap. If you take this one, its children are going to be these two elements, 17 and 16. That's okay too. And then if you take this one, its children are going to be these two, 15 and 13. And then if you take the element 17, which has the index 1, 2, 3, 4. So the left and right children are 14 and 18. Now you can see where the problem is. This 18 is not supposed to be here. Because in a max heap, the child is always greater than or equal to the child. So therefore, that is the correct answer. Now this one is a heap by definition because it's just a sorted array. And so if you just put them in that order, like if you build it like 19, 18, 17, you do like a level or the traversal, you're going to get a heap. 13, 12, 11, and 10. All right. Okay. So let's move on. Okay. My next question is, how many compares are needed to build a heap with the keys 12, 10, 14, and 16? I'll put the poll back in here. This time I have 5 options. Okay, so I just published the polling results. So I think it looks like you are between 3 and 4. Perhaps let's just work it out. So 12, no comparisons. I'm building a min heap. So I put 10. I have to do one compare and swap those two. And then I'm going to insert 14. But I got to compare 14 to 10 to make sure that they're in the right order. So because of that, I'm also going to do one comparison here. Right now it's a min heap. So now I get 16. I will insert 16. I have to compare 16 to 12 to see if it's a min heap or not. So in this case, it looks like it's in the right place because the 12 is less than 16. And so if you look at this this whole thing, that I only did one comparison. So the correct answer is 3. All right. Okay, let me check your. Okay, good. So so we get through that, and let's move on to the next one. Okay. So the next idea is implementation. How do we implement a heap? Now, clearly the idea is that when you have a heap, let's say you have a heap. So here's a min heap. So notice that I repeated 13 on the left-hand side because the heap, the only requirement is that the parent is less than or equal to the children. Now, let's think about how one would implement a heap. Implementation of a heap is using an array. Let's go like this. And so clearly we have the array elements indices are the level order traversal. So we have 10, 12, 13, 13, and 14. And let's assume that we're going to insert a new element into this. Let's assume that we insert 5 into this. So let's assume that we're going to insert 5 into this this structure. So 5 goes in here. That's the 6th location of the array. Now, what we need to do is we need to move 5 up the this array, because 5 is not supposed to be there. 5 is supposed to be here. So 5 has the index 6, because that's the index 6 here. All right. So what we need to do is to compute the parent of 5. So how do we get the parent of 5? How do we get the index of the parent of 5? Very good. Okay. 6 divided by 2. So I take the index, divide by 2, and then I see that this is the parent. So I compare 5 and 13. Because 5 is less than 13, I'm supposed to swap those two things. And so I'm swapping them in the array. So on the conceptual picture here, we have 5 here and 13 there. Now the 5 has index 3 now. 5 is at index 3. So how would you compute the parent of 5 now? Very good. So 3 over 2. 3 over 2 gives you 1. So the parent of 5 is 10. So we compare, one second here. Excuse me. We compare 5 and 10. And so the 5 is less than 10. So we're going to do a swap here. So in this case, how many comparisons we did, how many swaps we did? Excuse me. So we did at least 2 comparisons. And we also do 2 swaps. You don't have to subtract 1 and divide by 2, because remember that given I, the left child is 2i, right child is 2i plus 1. So if you take 2i and divide by 2, you get I. If you take 2i plus 1 divide by 2, you still get I because of the integer division. So therefore, there's no reason to subtract 1 from the value. You could just do that. Based on Java, if it's a Java thing. So you have to be careful here. Okay, so here's the code that does it. I'm not going to walk through the code, but basically what this code does is exactly what I did here. What I have is the array, and I compare, I just move through that. Okay, any questions? You always divide the index by 2 to get the parent. If you have a child, you divide by 2. If you have the parent, you can multiply by 2 to get the left child. You can multiply by 2 and add 1 to get the right child. Okay, so here's the code. You can take a look at it. It's not difficult to understand. So the other idea is the deletion. How do you delete something from a priority queue? So let's say we have this min priority queue or heap. All right, so we got this here. What we like to do is to delete the min. Delete min. Delete means we have to get rid of this 10. So the question is, who would be replacing the 10? So the way we do that is the following. We know that when you delete the 10, what's going to disappear is the last element in the array, this one here. So basically what we do is we swap these two elements. So 10 comes here and 20 goes there. Okay, because the last element is easily deleted, because essentially what you have is an array like this initially. Initially, it will be like this. Okay, this is what we had. Okay, so we had 10, 12, 20, 16, 15, 30, 20. So we have, and so we're going to swap these two first. So that means we take the last element and the first element, and then we put the 10 here and put the 20 here. Notice by doing that, I can just get rid of that. The heap size is reduced now. So basically, if I want to delete 10, what I need to do is swap that with the last element in the array and then do something with it. So for example, the 20 now will go here. All right, so the heap is one less now. But what I need to do is to make sure that this is going to come down if it needs to come down. Now note that this is not a min heap anymore, right? Why is that? Very good. So these two are not in the right place. So basically what you have to do is once you swap it, you have to compare this with both of these. Because the reason you have to compare with both of these is that you got to find the minimum of the two children. All right, you cannot compare with one of them. And then you swap those two. Because 12 was the minimum among 12 and 20. Note that if you had maybe 5 here, yeah, it could have 5 here, right? If you had 5 here, then you would be swapping with 5. All right. So that's why you have to do 2 comparisons. So notice that to sift down, you have to do 2 comparisons. And so now you do another comparison to make sure everything is okay. It's not okay. So you have to swap those two. You get 16. All right. So now it's a min heap because every parent is less than to that. So the difference between sifting up, where you had to do only one comparison, because you only have to compare with the parent, but going down, given the ith index, you have to compare with 2i and 2i plus 1. All right, so you have to do 2 comparisons to do that. Okay. Okay. So here's the code again. This code is a little bit more involved. We can just take a look at it. I doubt that you will be asked to implement a heap, but you should know the idea. In other words, once you look at this idea, you can do it yourself. It's not that difficult to implement this. There's a lot of code that's been done already, so you don't have to write your own thing anyway. Okay, so I'm going to write some answers here. And so you can think about what the right answer is. I'll put the poll up here. All right, so let's give it a try. Okay, looks like so far, let's see, let's wait a little bit here. Okay, so here are the polling results. Oops, did I publish it? I think I published it. No polling. Oh, how did I miss that? Anyway, so the correct answer for this one is, second here. I'm missing the chat here. Okay. So the correct answer for this is n log n. The reason it's n log n is that you have a min heap. Let's say you have a min heap like this. Wouldn't be that. So 16. Okay, this is 15. 8, 9. Oops. Right. 18 and 19. So this is a min heap. All right. And if you convert it, what you can do is you can delete min and insert to a max heap. So max heap is doing the opposite. So 12 is fine, and then the 12 will be replaced by the next element. So 19 will go here. I'll just do a little bit, just give you the idea. So 19 goes here, 12 goes here. So 12 is deleted. And then because it's a min heap, 19 is going to come down. So 14 goes here, 19 goes here. And then 19 comes here, 18 comes here. So it comes down. So deleting an element is log n time. And inserting an element is also log n time. So if you do delete and insert, it's going to take n log n time. Okay, because you are doing n elements, you're deleting and inserting it. So in fact, you can just say deleting an element from the min heap is log n, and inserting element to the max heap is also log n. So it takes 2 log n to do one element, but if you do n of them, it's going to be n log n. Okay. So this one is kind of hard because you're asking the question, if you're given a heap, how would you, let's say this is 15, 16, 18, 20. Okay, so that's a min heap. And you want to search for a specific item. Let's say you want to search for 15. And there's no easy way to search the heap, because first of all, we don't know which side the 15 is in. It could be on either side. It's not a BST, so we have no idea which side to go. So essentially, in order to search for 15, you have to search all the elements. That's the only way to do it. So in other words, so let me ask the question then. If you search, is it big O of 1, big O of n, big O of log n? What is the search? How do you search for a specific priority element in a heap? So let me just add the poll here. I have 3 of them here. Good. So looks like most people are picking B, which is correct, because if you're searching for the element, then we have to look at everything, because we don't know which side it's going to be in. So we might look at array element 1, and then 2, then 3, then 4, then 5. So you have to pretty much look at every element to find this. So it's correct that the answer is really this. Okay. So the next question is, suggest a sorting algorithm let me just make this a little bit with the window here. So just a sorting algorithm that uses a heap. So for example, let's suppose that we have a min heap. Take the same 15 and 16, 18 and 20. Now, min heaps are not, if you look at the array that store this heap, they look like this: 12, 14, 15, 15, 16, 18, 20. In this case, we were lucky that it turned out to be that, but it doesn't have to be sorted. Now you can see that the array is already sorted if you look at this, but it doesn't have to be. Okay, because it's possible that you could have a 15 here, and that's still a heap. And that means you will have a 15 here. Now the array is not sorted. Okay, so although it's still a min heap. So one thing we could do is that in order to sort things, what we can do is we can do the following. We loop, what we do is delete min n times, and sort of insert that to the end of, into another list or something. That's fine, right? So we take 12, delete min, that's 12. Then the next delete min should give you 14. The next one should give you 15. The next one should give you 15. The next one should give you 15 again, because the heap would have adjusted to this delete min. All right, and then the next one would have given you 16 and 20. So essentially, if you loop n times by doing delete min, you can get a sorted array. So if you loop n times and you delete min n times, what is the complexity of the, this is called heap sort. In fact, what I just did is called heap sort, because the heap sort is that you build a heap first, and then you perform delete min or delete max n times. And if you go with the same choices of the answers, 1, 2, 3, what is the complexity of this? Is it n log n or n log n? All right, so let me turn the poll on here again. Okay, so the question I'm asking is that what is the complexity of this operation of heap sort? Okay, great. Looks like most people are going with n log n. Great. The answer is correct. It's n log n. That's the correct answer. And about half the people chose that answer. Okay, because it's n log n, because delete min is a log n operation. Okay, why do you say it's log n? Because the height of the tree is log n always, because it's a very compact tree. And so if you delete something, you only have to come down the tree. So it's only log n operations to delete something. Same thing with insert. This is one of the nice things about heap, is that insert is log n, and delete, we usually do delete max or delete min, is also log n. We don't delete random numbers from a heap. So insert and delete are log n. So if you loop n times log n operations, that would be n log n. So that's correct. Okay. Now, one might ask the question, how long, what is the complexity of building a heap? We know we can build a heap in n log n time. I don't think that's hard to understand. Okay, so we can definitely build a heap in n log n time. That's because we have n things and we perform n inserts, and because we know inserts are log n time, if you do n inserts, then it's n log n time. But can we do better? What we mean by better is, can we do it in linear time? So let me give you an idea that you can think of. Let's suppose you're given some random array. Okay, let's say this is 10, 20, 5, 6. I'm just putting random numbers here. 10, 15, 30. Bunch of random numbers. Now, you can think of these random numbers as a random tree. 10, 20, 5, 6, 10, 15, and 30. Now, clearly, this is neither max heap nor min heap. It's just a random array or random tree. Now, if I want to build a heap out of this one, what I can do is I can I can do an algorithm like this. I'll start with this one. 30 is in fact, if you look at all of these leaf elements, they're already heaps by themselves. If you just consider them, let's suppose we're going to build a min heap. Okay, so they're by themselves. But if you go to the next level, if you start from this one here, what you need to make sure is that you want to make sure that this part is a min heap. So all you have to do is just compare element to its children. So you do 2 comparisons and you realize it's in the right place. 5 should be there. And then you move to this element and you look at this part and try to make it a heap. What do we need to do to make that part a heap? The left side here. Can you type some answers into the chat? Okay, we want to swap 6 and 20. That's correct. So we swap 6 and 20. So now if you look at the things that I have looked at, the left tree and the right tree, they are both heaps by themselves. Now we look at this element. And that element, we check to see if it's a heap or not. We look at its children, 6 and 5. And what should we do? Okay, so you take the minimum element from either side. So you compare 10 to the minimum of 5 and 6. And because 5 is smaller, we'll swap the 5 and the 10. Now notice that I did fix the heap. So now it's a heap. So if you redraw this, so now it's a min heap. Now, because it's a min heap, I could do heap sort, all of those things. I think the proving that this takes linear time is more challenging. That's why it's a challenging thing. Now, here's what the argument would be. Elements on this level, which are 1, if you send them down, they only go 1 level down. All right, so typically we think like this. Maybe there are 2 to the power n elements here, 2 to the n minus 1 here, 2 to the n minus 2 here. In this case, let's assume that n is equal to 2. So that means level 0 has only one element, 2 to the 0. Level 2 has 2 elements. Level 3 has 4 elements. And these 2 elements, or 2 to the n minus 1 elements, we only push them down 1 each. At most, they have to come down 1, shifting down. The elements above that, there are 2 to the n minus 2 of them, have to come down only 2. All right, so again, you don't need to understand this completely, but if you are interested, it's a good mathematical thing to do. In fact, if you what you're going to do is, if you really want to do it, don't worry about it. You have to prove that 2 to the k minus 1 times k summation over some k is roughly proportional to linear time. But let's just leave the details without having to worry about it. I highly doubt that you'll be asked a question like this in the test. Okay. So here's an exercise for you to think about for next time. I will go over this next time when we meet on Thursday. I want you to think about a special data structure using 2 heaps, such that you can insert or delete in log n time, and you can find the median in big O of 1 time. Because finding the median is the middle element. So you want to design a data structure so that median element is very efficient. You can find it in big O of 1. But you can also insert and delete and retain all of these things in log n time. Okay, so it's not so easy to do with the regular structures. So, but if you use 2 heaps, you might be able to accomplish this. Okay, the second exercise also, I'll leave it as something for you to think about. Given a heap, we can insert or delete in log n time, but it cannot update the priority in a node. Okay, how can we update the heap priority of a given element? So something like this. Say we have 40, 30, 45, 43, 30, 32. So that's a min heap. And let's assume that we found an element, let's say 43. We update this thing, update its priority to 5. So now what we know is once we update the priority to 5, the 5 cannot be there. So 5 have to go up. Okay, so 5 will be first swapped with 40, and then swapped with 12. So the heap is going to look like, the new heap is going to look like this. Okay, 45 and 40. All right, so you can see that I could easily do this if I can find the element, right? But the problem is finding this element is not easy because we don't know where 43 is. Could be on the left tree or the right tree. We have no idea. And therefore, you have to spend linear amount of time looking for it. There's no other way. The other thing you could do is to use hash tables. You might want to think about how to do this using hash tables. Could we do a more efficient way to look up and change it? Okay, so that's for next time. Okay, our next topic is a topic called graphs. All right, before I move to graphs, do you have any other questions that I can answer on heaps? Yes, the previous question will not be on the test, build heap. I think I would not go into that because implementing a Huffman tree using a heap is, you could do that. Basically, what you do is with a Huffman tree, you have the nodes with the counts, you put them into a heap, and you pick the two minimum ones, and then you combine them and insert back into the heap. The priority queues are essentially the, heaps are the data structure that is used to implement a priority queue. So they're pretty much the same idea. Yeah, let's talk about that, the upcoming exam on Thursday, a little bit more on that. Okay, let's move on to the next topic. So the next topic is really important. Important in the sense that graphs are the big structure that is used by every application you can think of. So a typical graph, you might think, is a collection of nodes or vertices. So we call them nodes or vertex, connected by what's called the edges. And typically we say a graph is a structure that contains vertices and edges. So you can think of graphs of people connected to. So you might define the edge is a relationship between two people. You could define that as a friendship on Facebook or something like that. There are many things you can use. It's very generic, so therefore it's very powerful. So the edges are the things between the nodes or the vertices. All right. And when you get to large graphs like Facebook graph or something, you might find things that are clicks. Okay, so the clicks are the ones that you have all these islands of connected components. So you might imagine that all the Rutgers students are going to be maybe, within Rutgers, you're going to find a lot of cliques who are friends of each other. So they are all connected together. And then if you go to some other place, you might find another cliques and so on. Then you can find you can say, okay, that's the Rutgers clique. This is the Princeton clique, whatever. Right? So you could define it in a lot of different ways. So as you can imagine now, a relationship in real world, like a Facebook graph, is represented using an abstract concept called graph. And here's another graph. Now in this graph, it's an airline route map. So notice that the graphs, in this case, what are the nodes and what are the edges? So you might say nodes are the cities. In this case, nodes are the cities. And then edges are the routes. Edges are the routes. And so when you define the route, you can say, you can have a weight for the route. So for example, you can say the distance between Honolulu and Los Angeles is, I'm not sure exactly how much it is, but let's say 1,000 miles. So it's assigning a weight to that edge. Or you could also define the edge as the cost of flying between Honolulu and Los Angeles. Let's say it's $250. So by looking at this type of context, you can understand a lot of different questions. Like, for example, you might ask the question, what is the minimum cost of flying from this node to that node? So that requires you to first of all, find a path. You need to find a path from one node to the other. Then you might ask the question, what is the distance from this node to that node? To do that, you would add up the sum of the distances. Or you might ask the question, what is the cost of flying between those two cities? you might add up the cost of each of the legs of this flight. Okay, so you can see that the way we're doing this, it's very useful, the concept of a graph. In fact, graph is the most important data structure in computer science. We talk about weighted and undirected graphs. Like, for example, this is a graph of a bunch of nodes, and they're connected, but they have no direction, meaning that if B, in some ways, you can say B and H are connected. So you can say there's a flight between B and H, and also H and B. So they are undirected. That means there's no arrow defining the direction between any of these two things. For example, you can say friendship would be an undirected graph, because you might imagine if A is a friend of B, B must also be a friend of A. Otherwise, there's no definition of friendship there. Okay. And then we have what's called directed graphs and weighted and directed graphs. So the directed graphs have edges that are directed. So that means it shows you not just the cost of going between one node to the other, but also the direction that you can go. So you might say, if I want to go from some node to some other node, so let's say I will start from here, get some color here. So I'll start from here, and I can ask the question, can I go to this one, to D? How can I go to D? Can you find a path from A to D? And if you can find a path, can you make sure it's the minimum path? Okay, so some people are writing A to F to D. Okay, so to go from A to F would cost me 0.9, and then F to D would cost me 1. So it's a 1.9 cost route. Are there other things? Okay, there's another one, AEFD. AEFD. Okay, so A to E would be 0.1, E to F would be 0.45, and F to D is 1. In this case, it would cost me 1.55. Oh, that's a good one, right? That's a better route. In fact, that's at least you have more legs, but it's cheaper. It's 1.55 total cost. There are other costs like ABD. Let's look at ABD here. So A to B is going to be, we can go from A to B. All right. Anything else? Yeah, okay, good. So I think that this kind of gets you the point. Okay, the point is that when you want to go from A to D, there can be multiple paths. And some paths could be shorter than the other paths. So soon, like next week, we're going to learn the shortest path algorithm called Dijkstra's algorithm, which will tell us how to find the shortest path from one node to the other. Now, you might imagine that's the most useful results that allow us to run our Google Maps, for example. You go to Google Maps, you want to go from point A to point B, Google Maps will find you the shortest distance or shortest time, or you can even get you can get country roads, highway, all of that stuff. Okay, so there are a lot of things that can be done with this kind of an algorithm. But we will talk about the shortest path algorithm next time. Okay, so the question we're asking next is that how can we represent a graph in a computer? Because the graph is essentially a concept. It's a concept that contains edges and vertices. And so we got to find a way to represent this in a computer. In other words, in a data structure, we have to represent this. So the first thing I'm going to talk about is representing the graph using what's called the adjacency matrix. So let's take a look at this graph here. Suppose we have A, B, C, D, and let's draw this, let's draw that, let's draw this, and I'm going to put some numbers into these things. So what I drew was a directed graph. All right, our nodes are called A, B, C, D. Nodes are called A, B, C, D. Let's name them as 1, 2, 3, 4. Because you can take any nodes, like for example, cities, you could name them 1, 2, 3, 4. It doesn't define any order, but it just gives you a way to enumerate the nodes in a graph. Then what I will do is I will use what's called a matrix to do this, to store the graph. So let's suppose that we take a matrix which is 4 by 4. And could you think about what I would do with this matrix? How would I store this graph in this matrix? Any ideas? Okay, so one idea is connections are 1, no connections are 0. That's a good idea. Okay, values of traveling from. Okay, great. So let's do this. I think what we're going to do is we know that A is 1, B is 2, C is 3, and D is 4. And so if you have A going from A to B, that means A to B. So this from this side, A, B, C, D. So A to B is 1. So we're going to put a 1 here. Okay, and there's nothing else from A to B, A to anything else. From B, we can go to C with a cost of 3. So B to C is 3. And then from C, we can go to A with the cost of 4. And I can go to D with a cost of 2. And from D, I can go to B with the cost of 2. I can go to C with the cost of 5. So essentially, I could represent this as follows, like a matrix. So if things are not defined, I will leave them empty or put like a -1 there. But you can see that the only defined things are these. Okay, and so now what we know is that the graph on the left and the matrix on the right are the same thing. The only difference is that we can draw this, but we can put this in the memory. Okay, so what we need to implement a graph is then a matrix. So we need a matrix. Okay, space utilization. So how much space is taken by my graph if you assume that each integer is 4 bytes? So someone says 24 bytes. You can type more answers. Maybe I'll write some answers so you guys can. So I'll write 24, and some others are saying 64, and say 16. And let me turn on the polling here. And the fourth choice would be, let's say, 32. Okay, looks like you're doing well. Looks like most are choosing this option. In fact, that's correct because there are 16 locations and each one would require 4. So the answer would be 64. But if you really think about it, out of this 64, we only use 1, 2, 3, 4, 5, 6 integers. So the allocated memory is 64. What is the used memory? So the used memory is only 1, 2, 3, 4, 5, 6, 6 integers. So the used memory is only 24. So the allocated memory is 64, but the used memory is 24. It seems like very inefficient way to store things. In fact, this matrix is called what we call a sparse matrix. That means more elements are not utilized than elements that are utilized. So there's a better way to do this than just putting them in a matrix. All right. So next time we're going to talk about that. Okay, that idea is called the adjacency list. We'll bring some examples and we'll talk about some algorithms involving these things. Okay, let me go back to the chat here again and ask you questions about if you have any questions about the lecture. Okay, I think it's great. Hopefully, you guys got something from this lecture, and I'll have this also saved on Sakai. So we'll see you on Thursday. Office hours are going to be online. They're on Thursdays. They're between 4 and 5. I'm fine. Thank you very much, Sean. If you have any questions, you can type it in. We got 4 more minutes. If you want to ask me anything, that's fine. I'm staying healthy. Thank you. I'm trying to be very careful with travel now because things are not looking good. I hope you're doing the same. What recipes do you recommend for a healthy breakfast? Okay, that I don't have any ideas because I don't eat breakfast, which is a bad thing. I don't recommend that for you. Thank you very much, Sean. I appreciate this is something, if you have any concerns about this, I think I've figured this out, although I still don't like it. I rather be in the lecture hall and looking at you guys. Yeah, so I think in terms of, like I said, thank you for appreciating my efforts, but I think it's it's a tough thing to go through for all of us. I think not just for me. I think you guys have to kind of adjust to this as well. It's not easy, and especially the motivation factor. I think that's my biggest thing, to get myself motivated to come and give a talk like this. It seems like I'm just talking to a computer, you know. All right, so if you have any questions, you can. I will stay here for a few more minutes. The technical issues, no. I think for the most part, Big Blue Button seems to be working for us. So that's great. I didn't really know anything about this product until now. It's an open source thing, so uh, I guess someone need to set it up, and looks like they have done a good job setting it up. And I don't have to use Zoom anymore. I think Zoom is not designed for lectures like this. I think it's designed for meetings.